Hello, hello. Am I audible? Hello, hello.
Yes, sir, you're audible.
Okay, okay, great, great. So yeah, thanks for confirmation. So let us begin from where we left off in the morning. I'm going to yeah. Okay, thanks, Roshan. So let us begin from where what we were doing in the morning and from yesterday. What are we doing? Is that we are solving and we are seeing our first quantum algorithm which theoretically gave some nice results and proved that quantum computers indeed have computational advantage over classical computers. And then we saw a very simple problem, which is to find out the constant, if a function is constant or balanced, if an unknown function is constant or balanced. And then in the morning, we solved for Deutsch algorithm. We saw the Qiskit implementation, which was very straightforward. We were aware about the oracles and everything. And also, we saw that in Deutsch Jodza, we have a very similar kind of structure, and we have constant oracle, balanced oracle. Again, we will have the same concept, but this time there will be multiple inputs. So let me start sharing, and let let us now focus on the quantum circuit analysis of the Deutsch Jodza algorithm. Okay, so let us go forward with the, is my screen visible?
Yes, sir, it's visible.
Oh, okay, okay, thanks, Shalini, thanks. So now let us move forward with the Deutsch Jodza quantum circuit analysis. So let us see the Deutsch Jodza quantum circuit, right? So very similar to what we have done in Deutsch algorithm, but this time we are going to use the compact Hadamard gate equations, right? If you recall, in the morning we have studied what happens when Hadamard is applied to n qubits, right? And I mentioned that these are very important. So actually now we are going to use them. Okay, we are going to use them here directly. Okay, so this is the quantum circuit analysis. Now let us begin. So again, we will start with our ket 0. So we have started with ket 0, but this time we have started with ket 0 tensored n. That means all the n qubits have ket 0 being initialized to ket 0. And this is our input, or the first register. So I have already explained this while I was explaining you the oracle construction in the morning. It should not be too difficult. Then already we saw that we will be applying Hadamard gate as well. So Hadamard and to the power tensor n, that means apply Hadamard to all the n qubits. Okay, and then again we saw that we also have the second register as well, which where we also apply Hadamard to create superposition. So this is what we call the output, or the second register. Okay, and therefore, like, if the first one has first register has n qubits, then we have another qubit. So therefore total, as I mentioned you, it will be total will be n plus 1 qubits. Okay, and then what we are going to do, we are going to again draw the oracle. So we draw again our unknown function. It takes inputs x, y, and we encode, we, let's say it's uf, and then again the same notations, y, x, or fx. So let us see, like, somebody is joining. Let's see. Okay, you just admit. Then, like, then again we have, again the structure is very similar. Okay, so you can compare it with the structure which we have in the Deutsch algorithm. Very similar. Again we will have measurement. And that's it. Again, here we do not do anything to the second qubit. Okay, so again, let us break the circuit in parts. Okay, again, let us draw these dotted lines and let us break the circuit in parts, because again we are going to do analysis and then we are going to see the Qiskit implementation of this, and that will conclude the class. Okay, so let us see the analysis of this. 0, 1, 2, 3, 4. Okay, 0, 1, 2, 3, 4. These are the steps. So let us also name them. Phi 0, this is phi 1, phi 2, phi 3, and phi 4. Okay, now let us start doing this step 0. Okay, so let us do step 0. Again, the same technique, like, this, all the algorithms analysis can be done in this way only, like how I have done. Break the circuits into several parts and then solve it step by step. That is how you should always do, because that helps you understand conceptually, right, like how you are going through step by step. So initially, again, we start with that. Initially, we prepare the state. Get phi naught is equal to 0 tensored in, and then 1 in the second register. Okay, so first register has all these zeros and second register is 1. So just very carefully just observe the similarity. It is very, very similar to what has been done in Deutsch algorithm. The only difference will be, now this time we are going to use compact expression of Hadamard gates. Okay, Hadamard applied 10 qubits, which we have already studied, and the general format of the Hadamard gate, right, like Hadamard applied to ket x. Okay, and I boxed those expressions. It is because of that reason only, because we are going to use them, and we also use them in other algorithms as well. It's not only about this, but even in other algorithms also you are going to use the same Hadamard expressions. Okay, Hadamard applied to multiple qubits. That's one of the fundamental steps. Okay, so then step 1, apply apply Hadamard. Okay, apply Hadamard gates. That's it. Apply Hadamard gates. Gate phi 1 will be equal to, and then H tensor n will be applied to 0 tensored n. That means apply Hadamard to all those 0 qubits. But also you have the second register, right? So therefore, let us not forget that Hadamard is applied to ket 1 as well, right? Because the second register has been initialized to ket 1, right? And it always consists of only a single qubit, right? As we have seen in the morning, always consists of a single qubit. Then what will happen? Hadamard tensor n applied to ket 0 tensor n. I have written that formula before in the morning. Okay, so just take a look at your notes, flip back pages in your notes and check what is the formula. What is the formula for that? 1 upon under root 2 to the n, and I'm going to write the decimal notation. Okay, x is equal to 0 to 2 to the n minus 1 get x, right? That is the formula which I have defined, right? So I've just directly used. Okay, just be careful what formula we are using. That is what you need to be careful here, and even for the other algorithms as well. That means this formula will also be useful for Simon's algorithm, Bernstein-Vazirani also. Now what will happen now? Then we have the Hadamard applied to 1, which is ket 0 minus ket 1 divided by root 2. Okay, and this is what, this is, you already know, this is the ket minus state. Okay, we can write it in short, or if you want to write it fully you can do that, but like, you can write it in short, because I mean you all are aware, right, what is ket plus and ket minus. Now step 2, what will happen to step 2? So step 2 will be the unitary application, right? So the unitary the UF unitary is applied, the UF unitary is applied to all the n qubits, okay, to all the qubits, and then uh, simultaneously, right? I mean, it is always simultaneously, but we solved it like sequentially in the last one, simultaneously. Okay, so let us do that. So let us say ket phi 2 is there, and then UF is applied to ket phi 1, and then what will happen is that you are going to apply UF unitary, and the formula for that is 1 upon under root 2 to the n. So when you apply, then you get this expression, which is all these values x1, x2, like all these inputs basically up to xn, okay, dot 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 up to xn belonging to. So this is I'm writing in binary format 0 comma 1, okay. So basically what does means x1, x2 are what, all those inputs, right? Because we have multiple inputs, okay, and therefore all these multiple inputs where each of the input belongs to 0 1, okay, we have this coefficient where we have -1 to the power fx and get x. This is the condition, and then also we have the get minus as well, which is going on. Okay. So this is the condition what we get when we apply the oracle to all these qubits, and this is the generic condition of the Deutsch-Jodza. So basically, this formula which you can see here, this formula which you are getting, like this stage, basically this stage which you are getting, this formula is the generalized version of the calculations which we have done in morning. Okay, the step 2, if you remember, you can flip back pages. In step 2 was very long, if you recall. Step 2 was very long in Deutsch algorithm, right? So this is the compact version of step 2. Okay, in Deutsch we cannot do for every qubit, right? Then we have to select a particular n and then do it, but that is impossible, that's infeasible to do it, right? Therefore what we can do is that we write it in this generic format rather than solving longer expressions, okay, and that's it. That is very simple. That's it, step 2. Now we apply step 3, where again we are going to apply the Hadamard's formula from the previous one. So step 3 will be apply. So once you are familiar with Deutsch algorithm, Deutsch-Jodza is very easy to understand. Only thing you need to remember is the Hadamard applied to n qubits. If you remember that expression, then everything is definitely much more better to understand. Okay, on the first n qubits, okay, we are going to do it on the first n qubits, right? Because there also what happened in Deutsch algorithm, again compare this with Deutsch algorithm. In Deutsch algorithm you applied Hadamard only to the first qubit, but you never applied it on the second one, right? That means second register. So here's second register also has one qubit. You are not going to apply Hadamard to that because we are going to not do any calculations at that, right? Therefore, you are only going to apply it on the first n qubits, which is the first register qubits. Therefore, what will be ket phi 3? With that thing in mind, what will be ket phi 3? Ket phi 3 will be what? Hadamard tensor n tensor I, right? In that step 3, if you recall, again flip back your pages and take a look at the derivation which you have done in the morning. In Deutsch algorithm you were having Hadamard tensor I, but now you will have Hadamard tensor n tensor I, right? Because you have to apply Hadamard to all the first register n qubits, right? That's why it makes sense, right? Just compare it with the previous expression, and this will be applied to ket phi 2, of course. And identity, why last in the identity? Because again, like we are not doing anything to the second register, and doing nothing means applying identity, right? It's equivalent to applying identity. So once you do that, then you are going to write this expression. So please write this expression carefully. This is a longer one. 1 upon under root 2 to the n, and then we have the summation where all the inputs x, okay, let us write it in short, 0 comma 1 n, okay, this is the short form. And we also have minus 1 f of x. And then what will happen? Hadamard Hadamard tensor n will be applied to Hadamard will be applied to ket of x, right? It will be applied to this one, right? From here, this one. Look at this. Hadamard will be applied to this one. You can underline this, okay? Here, what Hadamard will be applied, and what happens when Hadamard tensor n is applied to ket x? Look at the formula which we saw in the morning. What is the formula? 1 upon under root 2 to the n summation. Let us take a different variable. In that formula, I took y variable, x dot y. Remember? So here, let us take a different variable just to not get confused. So let us take a different variable. Let's say z and minus 1 x dot z get z, right? And also we have the minus also. It's going. Okay, so this is the expression, okay, which this is the expression which you get when once you apply Hadamard tensor n to a general state get x, and I have given the formula for this in the morning. I have directly utilized that formula. Okay, so you can see the whole analysis of Deutsch-Georgia is just about putting the correct formula. That's it, nothing else. Okay, so do not be scared by these expressions. These are not scary expressions. These are just generalized concise expressions. Okay, whenever you are dealing with multiple qubits, you cannot write all the qubits every time, right? Then you need to deal with concise expressions, right? That's why we are writing in this way. So if we solve further, then we will have ket phi 3 will be equal to 1 upon, so we have on 1 upon under root 2 to the n, 1 upon under root 2 to the n, so we will get 1 upon 2 to the n. So let us take it out, and then summation, let us take z belonging to 0 1 n, okay, and let us take this summation inside, which was x belonging to, so we are just rearranging terms, okay, not doing, this is not mathematics, just rearranging terms. Okay, we are not doing any calculations. F of x, because minus 1 is present in both the summations, so that's why we are rearranging terms, x dot z. Okay, and then get z is also there, and also this minus is also there. Okay, this is the step 3. So we are almost complete. Now what will be step 4? So in step 4 we will start doing the analysis. Okay, and the analysis of step 4 is very important. So uh, take a look at the analysis of step 4 carefully. Now with the step 3 expression, we are going to consider this step 3 expression for both the cases, constant f and balanced f, just as we did for Deutsch algorithm in the morning, right? Constant f and balanced f we checked, right? If you recall, ket phi 3 was the last expression, and from that only we were deriving how the state is getting collapsed after taking measurement, what is the state we receive in the final measurement, right? So similarly, now we will have step 4 where we are going to do the same, and I'm going to do it here. Let us say step 4. Okay, now finally measurement of first n qubits is made in the made in the computational basis, right? We are going to do it in computational basis. Okay, we are going to do, so we consider, now what we are going to do is that we will be considering the probability of measuring 0 on every qubit which corresponds to the term in the superposition. Okay, so let me write this statement, this is very important. We consider we consider the probability, okay, we consider the probability of measuring zero, okay, measuring zero on, so we are only going to get involved ourselves with whether zero, all zeros is coming or not, okay, we are going to involve with that. If something else is coming other than all zeros, that means the function will be balanced, okay. If all zeros is coming, therefore it is constant, okay. So therefore probability of measuring zero on every qubit, that is what we will be concerned about, which corresponds to the term in the superposition where ket z is 0 tensor n, okay. So therefore basically what we are going to do is that we are going to see if ket z, okay, if the ket z happens to be all zero or not, and it is going to happen when the amplitude of ket z is maximized towards having all the zero bit string, right? This is like, the amplitude matters, right? In quantum, amplitude matters. How will you how do you do analysis in quantum computation? The main part of quantum computation which you do is to analyze the probabilistic results which you receive at the end, right? Quantum computer gives you probabilistic results, okay, and now you need to analyze how many times the state appeared, right? So therefore here also we are going to do the same. So let us start doing that. Let us say we have constant f, okay. Now what we can do for constant f, we can factor out the term -1 to the power fx. Why? Because it is constant function, right? A constant is a constant. It's, you can consider -1 to the power fx something like a constant, like c, like capital C or something, okay. So and constants can be taken out, right? Whenever we are doing calculations, we take out all the constants and only deal with the variables, right? So therefore something like that you can do it, but in balance function you won't be able to do it, okay. That also we will see, but here we can factor it out. So what happens when you factor it out? So let us write the state ket phi 3 is equal to -1 to the power fx, which is now constant and factored out. Then we have summation z belonging to, this is the same expression which I wrote before, and then 1 by 2 to the n summation x belonging to 0 1 n -1 x dot z, and then also ket z, and this minus is also there, you can ignore it for some time, okay. We are anyways not dealing with that now. For for this result, for the ket z to have all these zeros, okay, right? We want the ket z to have all the 0 bit string. Why? Because constant function, right? For constant function, I already said you in the morning, right, that in the algorithm output you should have all the bit string 0, right? That is a constant. If it does not have, let's say if it have all ones, then it is a balanced, okay. Therefore that is why, so for that case we have, so if we have that case indeed, let's assume that we have that case indeed, then what will happen? 1 upon, so consider only this expression, okay. We are going to consider this primary expression, this one, okay. So let us write that out. So 1 upon 2 to the n x belonging to 0 1. And why we are considering that? Because ket, because this expression is attached with ket z, okay. X dot z is there, can you see? X dot z is there, so we are only considering the variables, okay. We are only considering the variables. Here, what is our variable which we want to be all zero? It is the kz, right? This is what we want to be all zero, okay? All zero bit string. That's why we are that's why we are focusing particularly on that. And remember, also remember that Deutsch algorithm, Deutsch-Georgia, it already involves quantum interference. Okay, and what is quantum interference? That's just nothing but the constructive and destructive interferences, right? Which you have studied already before. And therefore, that is why we are dealing with amplitudes, because constructive and destructive interference deal with amplitudes, right? Whenever the amplitudes get added together, then it is a constructive. When they get cancelled out with each other, then it is a destructive. And that is why here also we are dealing with amplitudes. Because remember, Deutsch and Deutsch-George algorithm both are based on the principle of quantum superposition. That means quantum parallelism and quantum interference. Okay, that's why special focus on amplitude. Always remember this. Okay, now x multiplied with, let's say, like, we have already said that kz is all zeros, so all zeros. Okay, so 0 dot 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 0. Then what will happen? 1 upon 2 to the n, and then summation x belonging to 0 1. Okay, and then minus 1 to the power 0, because anything multiplied with all the zeros is 0, right? And anything to the power 0 is what? Anything to the power 0 is 1, right? From basic exponents, anything to the power 0 is 1. Therefore, 1 upon 2 to the n summation 1, and then x belonging to 0 1 n, which will be whenever you sum 1, and you have to see like where this expression goes till. This expression goes till 2 to the n. Okay, this expression is actually going till 2 to the n. Okay, you can verify this in the formula which I have taught in the morning. So therefore, whenever you sum all of it, whenever you sum 1, then you are going to get the final result of the summation is 2 to the n. Therefore, 1 by 2 to the n into 2 to the n will be the result of this summation. Okay, 2 to the n. And then what you are going to get is the 1. You will get 1 times minus 1 f of x, which is there outside, and therefore the amplitude turns out to be either plus minus 1. Now what happens? This means, so let us do analysis. What happens? So this means this state k0 tensored n, and say minus is also there, has amplitude 1. Okay, we have got the result as plus minus 1. Okay, so therefore this state, okay, this state will either have an amplitude of plus 1 or minus 1, though, but the absolute value, but we are, remember, we are only focusing on the absolute value, right? So therefore the amplitude has 1. Okay, because why absolute value? Because you already know, whenever we take measurement and whenever we want to find the probability of occurrence of a particular quantum state, we take the absolute value square of that, right? So therefore, in that case, when you see, even if you have minus 1 and if you take the absolute value of that minus 1, it becomes plus 1 only. Therefore, this state has amplitude 1, and it can be concluded. And remember, what state has amplitude 1? Okay, this state, ket0 tensor n, and then ignore the minus for now. Okay, focus on that. Ket0 tensor n, focus only on the first register. Okay, ignore the minus for now. That is has been written just for completion purpose, but focus on the first register. Okay, that's where we are taking all the measurement, right? And therefore it can be concluded that ket phi 3 is equal to minus 1 to the power fx ket 0 tensored n, and minus has all the weight. Okay, therefore what it is trying to say is that this expression, ket 0 tensored n, everything is concentrated on this expression. Okay, that means the factor of amplitude is mostly concentrated on this ket 0 tensored n, and because of that factor of amplitude being concentrated, therefore it is a constant function. Okay, are you getting the point? Observe this, how we are now taking the amplitudes into the picture so much carefully. Okay, this we have also done. Okay, if you have seen in Deutsch algorithm also, if you observe the calculations carefully in Deutsch algorithm, we have only dealt with amplitudes only, right? We are doing the manipulation in the amplitudes, and that's why we wrote it as 1 minus f0, 1 minus f1, then f0 times some state. Why were we writing that? Because we are putting emphasis on the amplitude. Okay, because Deutsch algorithm utilizes quantum interference, and to deal with interference you need to deal with amplitude of the quantum state. Superposition it definitely has, because you put Hadamard, so therefore parallelism is already happening. But for the measurement purpose and for other calculations, you are taking the help of that support qubit which you have, and then doing amplitude analysis, which is just doing quantum interference. Therefore, so measuring first n qubits in computational basis yields the outcome ket 0 tensored n. Okay, with certainty of amplitude plus minus 1, which means that you have 100% probability of finding the ket 0, all 0 bit string in the first register, which means that the function is constant. Okay, so this analysis is a little bit more involved, but do not worry if you do not understand it fully. That is completely fine. You need to go through it once again. But once you start comparing this analysis with Deutsch algorithm, then it becomes much more clear and much more intuitive why we are doing that. Because even in Deutsch algorithm, if you recall, we were putting the values of f0, f1. If you recall, we were checking for f0, f1 individually. We were having the functions individually, if you remember, f0, f1, f2, f3. We were having 4 functions, remember, in Deutsch algorithm. And then we started putting those values like f0, f1 we put for constant, and f2, f3 we put for balance, right? A similar kind of thing we are doing here. But how we are doing it? We are doing it in a more generalized way. Okay, we are basically focusing more on the amplitude value associated with the quantum state, which is ket z, and checking whether that amplitude value turns out towards 100% or not. Even if it is not 100%, even if it is 90%, still majority of the time you are getting the bit string 0, and therefore the encoded unknown function is constant. Okay, this is very similar to Deutsch. Now what will happen when we have balanced? So balanced f, so we have done for constant f. Now balanced f, in balanced f we cannot factor out. Okay, this time we cannot factor out minus 1 to the power fx, as it takes different values depending on input. So basically it is trying to say the same thing. Okay, in Deutsch algorithm you saw that for the balance the output is dependent on the input, right? We were having 2 cases where you provided 0 and then you got 0 out. Okay, if you provided 1, then you got 1 out. Then in another case you saw f3 condition, you saw that if we give 0 we get 1, the opposite, and if we give 1 then we get 0 as the opposite basically. So therefore that is what we're trying to say. So we cannot factor out this minus 1 to the power fx, because now it takes different values depending on input. So it is no longer a constant, it is a variable basically. Okay, it is a variable depending on input x. So for ket z, therefore again we try to find out whether really we will be able to achieve a maximum probability of this 0 bit string or not, and you will see that we will not achieve. Okay, how? 1 upon 2 to the n summation x belonging to 0 1 n minus 1 to the power f of x plus x multiplied with all zeros. Okay, all zeros, 0 0, this is x dot z, right? So z is all zeros, but even if you put z is all zeros, still you are seeing that you are not achieving that much. Okay, because x belong to 0 1 n, and then you are left with minus 1 to the power fx. Therefore what is going to happen, since we are left with this, okay, this time we are not getting any plus minus 1 or anything. Okay, we are now getting only this expression 1 upon 2 to the n summation of all these things. So therefore what happens, therefore as f is balanced precisely, what will happen, half the terms in the summation above, half the terms in the summation f of x will be equal to 0, and other, because remember, like, it depends on the inputs, right? Like for inputs you have the output is dependent on the input. So therefore half of the terms, precisely like approximately half of the terms will be, output will be 0, and for the other half fx will be 1. So for the other half, and that makes sense from Deutsch algorithm. Again, compare it with Deutsch algorithm. There also we were having the same thing. 0 gives 0, 1 gives 1, but 0 gives 1, then 1 gives 0. If you combine both of the result, that means approximately 50% time the output will be 0, and approximately 50% time fx will be 1, and other half f of x will be equal to 1. So they cancel. Okay, so they cancel out, and the summation becomes equal to 0. Okay, summation, this is not plus minus 1, remember, the summation whole is getting cancelled because of that approximate presence of that fx is equal to 0 and fx is equal to 1. But if the summation is 0, then what will happen? The summation is the amplitude of the ket z state, right? It is the amplitude. What happens if amplitude becomes 0 for a quantum state? That quantum state vanishes, right? Anything multiplied with 0 into ket 0. What is 0 into ket 0? It's 0 only, right? 0 into ket 1. What is it? It's 1. It's 0 only, right? It's no longer 1, because the amplitude itself is 0. That means there is no probability. There is no occurrence of that state. Okay. Therefore, we can conclude that amplitude of ket 0 tensored n is 0. So amplitude, remember, amplitude of ket 0 tensor n is 0. That means ket 0 tensor n, this bit string has the minimal occurrence. Okay, that means the minimum probability of occurrence, which is what? 0 occurrence. Therefore some other state can appear, right? If not all, as I said you in the beginning, in the morning, if not this, then otherwise something else, right? Otherwise what was it? Balance. And now you got it. Okay, and we will never see all bit string 0 in measurement. We will see something else, and that means that something else means that this function is balanced. Remember, okay, how we are analyzing it with the help of amplitude. Okay, something else. Okay, remember, the amplitude of this all zero bit string itself is zero. Therefore, it will never appear. And that means itself that it is a balanced function. It is not a constant function. For constant, it is compulsory to appear, right? And that's why we got plus minus 1 amplitude with 100% probability that yes, the zero all zero bit string will appear. But here we are seeing no, we are not getting all those, and we are canceling it. All this summation becomes cancel. This goes out to zero, and once it goes out to zero, the zero is multiplied with that state get z, and everything turns out to be zero, and therefore that means the occurrence of get zero all zero bit string is minimal, and therefore some other state can appear. Let's say get 111 will appear. Okay, not all zero cannot appear. Okay, all zero cannot appear, but this can appear. Okay, and if this appears, that means it is a balanced function. Okay, very similar to what we saw in Deutsch algorithm, where we saw that if we have algorithm out versus get 1, then it is a balanced function, and if it is get 0, then it is a constant function. Okay, so this is the analysis of the Deutsch-Jodza algorithm. Now let us see this in practice, because once we see this in practice, then all these things will be more clear. Okay, so even if you do not understand it fully, do not worry too much. Okay, just understand the concept of this amplitude, that what we are trying to do with this amplitude thing, because this is the main concept of quantum interference. And also this concept is also used in Grover's search algorithm as well, which you are going to study later. Okay, so now let us see the Qiskit implementation of Deutsch-Jodza algorithm. Now again, what we are going to do is that we are going to import the libraries, as you are aware, and we are going to see for the constant oracle. So remember, what was constant oracle? So as I have mentioned before, so whereas constant oracle, yes, here. Okay, this table. We created this table in the morning, right? Input has no effect on output. We can randomly flip the output qubit register by applying X gates. Okay, so therefore that is the one which we are doing actually. For the case of consa, the input has no effect and we can randomly flip. So therefore we defined a random function from numpy. Np is numpy, right? NP is numpy. What is numpy? Numpy is numerical Python. What is numerical Python? It helps you to do numerical calculations using Python programming language, right? That is numpy. So from that, you took random and then you defined random integer, which randomly generates 0 or 1, which is random flips. So whenever this output, whenever you run this code, okay, whenever in the output you get 1, then you will apply the X gate on the nth qubit. Okay, you will apply X gate on the nth qubit. That means here you will apply it here. Why here? Because again, go back to your notes, look at this diagram here, look at my cursor here, this one. Here we are applying, right? We are applying the X gate into the second. We are applying it into the second register, right? Not into the first register. Remember, above ones are first register, right? We are applying it onto the second register. That's why we are doing it like that. Okay, and then once we draw it, okay, then what happens? Then you define your DJ circuit. DJ circuit is what? Deutsch-Jodza circuit. So quantum circuit n plus 1. Okay, that means all the qubits is n plus 1. If you remember, total number of qubits is n plus 1. I wrote it here again. Total is n plus 1. And comma n. Why comma n? Because you are not going to measure the second register. You're only going to measure the first n qubits. Okay, that's why comma n. Okay, n is what? N is, this is what? Second argument is classical bits, right? Classical register. And the first one is the quantum register, right? Now for qubits, so we applied the for loop basically for qubit in range n. Okay, for all the qubits you apply the Hadamard gate basically. Okay, and then you put the second register in the minus state. Okay, so that is what we do. I mean, that's what we are doing, minus state, by applying X gate first. First we flip it, make it get 1, and then we apply the Hadamard. So apply edge gates means we are applying edge gates to all the first register, and this is for the second register. Okay, this code is for the second register. Remember that. Okay, and then we apply oracle And this is the const oracle. So const oracle we have already defined here. Where is const oracle? Here is const oracle. Okay, here is const oracle. We have already defined that. And what we do is that we compose it. Simple. Take the Deutsch Georgia circuit, quantum circuit, and compose it. That's it. Okay, and once you compose it, you draw the barrier, and then again repeat the Hadamard gate. So this is how it looks like. So if you see here, nothing is there, right? So this time when we generated the random flip, at that time X gate was not applied. So basically random zero was generated. So output was basically zero. Since output was zero, therefore you have nothing. If output is one, then there will be X gate coming. And you can run this circuit several times to check. I will be sharing this notebook, do not worry. And then you should definitely play around with this notebook for some time. And again, this code is same. So I'm not going to explain this. What this code is doing, you all are already familiar. So I hope that by now you have already learned this code by heart also, if possible, because this is one of the code which you will keep on doing. Because remember, quantum computers give probabilistic results. So please remember that fact. Maybe you can note it down somewhere in capital letters. Okay, so as expected, we get the all uh, 0-bit string. So we measured only the first register. As you can see, Q0, Q1 is the first registers. This is Q2 is the second register. Okay, and we don't do anything to the second register if you see. And we measure only the first register. So we get the expected all 0-bit string, get 00. Okay, we get 00 as the measurement, which proves that the oracle chosen is indeed a constant function. Then you can generalize this. Okay, this is a way of generalizing it. So what you can do, what do we do in generalize? Again, you defined your quantum circuit. You take this condition of random, okay, by randomly flipping, whether randomly applying X gate or no X gate, like identity basically. Then what you do is that you do this new operation. Okay, what is this operation? Oracle gate const is equal to oracle QC. That means your circuit to a gate. That means it will look like an operator. Okay, it will look like a gate. Actually, when you apply this, it will look like a gate, and you can give that gate a name, just like you have X gate, Y gate, Z gate, right? So therefore you are converting this circuit into a gate. Okay, and you can do that, right? Why? Because all the quantum circuit operations can be composed as an operator, right? They are they are nothing but linear transformations. That's why you can do that. And once you do that and run this circuit, okay, this is the algorithm where you have the output qubit means second register. Okay, output qubit means second register. And then you set up the input register, the output register. Okay, and then you append this oracle. Okay, and once you append this oracle, then you will get the then you apply the Hadamard gate, and then you are going to get this circuit. Okay, look at this circuit, look at this nice circuit. N is equal to 8. Okay, N is equal to 8 qubits. Can you see? That means the first N, that means the first register. Look at this, this is the first register. It is 8. Okay, this is quite a large one, I know. You can maybe try it for 5 or 6. Okay, this 8 is quite a large number. But anyways, like, I'm just trying to show you, like, you can increase the number of qubits up to 32. This is 8, and then in the last one you can see that we have applied X. That means we have ket 1. Last qubit is the second register. So this is the second register, and all this is the first register. And as you can see, this is the oracle constant. If you see, we named it here, right? This name. If you change this name, A B C D E F G H or something, it will appear here. You can try to do it after I share you the notebook. Okay, this is how you can make a circuit look like a gate. Look at this pink box, it looks like we are applying some gate, right? It is very similar to, like, Hadamard gate. Hadamard is very small box. Okay, because it's a single qubit, but this is applied to all the qubits, remember. So this is like a bigger gate, you can say. Okay, a big gate, right? This is a bigger gate. And then you apply measurement to all the qubits except the second register, which is Q8. Okay, that is what we are doing. And here we are doing what? We are just calling all the functions. So we made the functions, okay, which is DJ Oracle const. We called this function, okay, and then we provided that, okay, we provided this Oracle gate const, okay. We prepared this thing, basically we prepared this box, okay. and we provided that box into the algorithm. That is what, and we provided the number of qubits also, and then we drew the diagram. Okay, this is for n is equal to 8 qubits, and this is a constant oracle. Okay, and again, like as you can see, of course, like you are bound to receive all zero. As we have analyzed it already, we are bound to receive all zero bit string. Okay, everything is zero. See, there is no one. Therefore, this has the maximum amplitude of occurrence, right? As per the measurement analysis which we have done right now. Okay, now let us see balanced oracle. So if the measurement of input is not a zero state, that means the amplitude of this all zero bit string is zero, which we saw the summation cancels out because of the balanced nature. Some of the outputs are zero, some of the outputs are one, and the sum cancels out. Therefore, the function is balanced. On the other hand, if we measure the state all zero bit string, then the function is constant. Okay, so therefore let us set the length of the n bit input string. So let's say n is equal to 2. Let us take it simple. Okay, let's try to do it simple. You can do it for 3 qubits also. For inputs 0 0, and now we are going to do this technique which we have seen before. So this technique, where is it? Yeah, input 0 0, we are going to do this circuit. Okay, this one, look at my cursor here, this one, right hand side. Okay, we are going to do that. Inputs are states q0 q1, which correspond to first register. Q2 corresponds to the output. This you already know. The oracle circuit is shown here. So let us define our bit string. Let's say we have the 0 0 bit string. Okay, and we will put x gates whenever the bit string is 1, right? As I told you, we will be putting x gate. Look at this, input 0 1, we will put x gates. We will wrap the c nots with x gate whenever the bit string is 1, right? So this is the function for that. Okay, this is the function, but it's very easy. This is, don't be afraid of this function. Okay, this is very easy. We are taking the length of this bit string. Okay, and with that we are running the loop, because we want to run the whole loop till both of this, right? We need to run the loop for the whole bit string, and whenever the bit string, if b underscore str of the qubit is equal to 1, that means whenever the bit string is 1 in value, then balanced oracle dot x qubit, that means balanced oracle, that means onto the quantum circuit apply the x gate onto that particular qubit. That is the meaning of this function. Okay, not function, sorry, this is the meaning of this code line. Then barrier, then again control not gates. So you will put the c not gates, then again you will put a barrier, and then again you are going to place x gate, right? We have to put x gate both the times, right? Not only one time. Look, it is not only one time, but we have to wrap it, like as I've said you, we have to wrap it, right? Okay, so I don't know why this is not working. Okay, yeah. For different input values, just wrap selected controls of input register with X gate. Okay, remember this wrapping. You have to remember the wrapping process. Okay, and now you can draw, and you can draw with different styles also. Okay, I think I might have not told, or I don't know whether you have been taught this or not, but I forgot to tell you. You can actually use the IQ. What is IQX? IQX is IBM Quantum Experience. Okay, that is the full form. What is IQX? IBM Quantum Experience. That is available in the cloud. You need to make your own IBM Quantum account to access it. IBM Quantum Experience, IQX. Okay, so if you do that style, then your circuit looks like this. Look, this looks a bit different, right? And look at this circuit, this looks a bit different, right? So the appearance is different. This is what kind of appearance? This is the IQX style appearance. Okay, this is the IQX style appearance. These kinds of things are asked in exam actually. If you are willing to give the exam, some of you might be willing to give the exam of IBM Quantum Developer. They ask these kinds of question, that what will happen if you have this style IQX, and maybe in the MCQ they will put this circuit and put some other circuit, other different looking circuit, and then they will ask you that if you run this code cell with style IQ, what will be the output you get. Okay, so like these are asked actually, these are Qiskit features. Okay, and you definitely need to know them, right? If you are willing to give this exam, you should definitely know about some of the Qiskit features, right? And knowing Qiskit features is beneficial to you yourself only. Okay, you are not doing it for anyone else, but it's beneficial to you only. You will find, like, shortcut ways of doing extensive calculations and making programs or algorithms by yourself, if you know, if you are aware about the Qiskit features. Okay, then we have the full circuit. So again, we apply the Hadamard gate to all the first register, then we prepare the second register, then we apply again, we compose. Okay, and this time also style IQX. Look, this looks so different. Here the measurement box is silver, but earlier in only MPL it was black, right? Hadamard gate box was blue. Okay, you can check, but here it is red. Okay, X gate was also blue or green, or I think something like that only. Here it is dark blue. Okay, C naught gate was light blue in MPL, but with style IQX, IBM Quantum Experience, you have this dark blue. Okay, so it just looks little bit more like, this is a more nicer representation. Like, it looks so nice, this one, right? So you can do all these kinds of things. Like, the more you explore, the more you spend time on these kinds of things, the better you get to know about Qiskit and its features. And it's also very interesting. It helps you with your research work as well. For example, you can plot these kinds of circuit in your paper as well, right? You can save it as an image or something and just plot it in your research paper, so that you don't have to draw it in latex. You can of course draw it in latex also, but yeah, that's again a different thing. Anyways, yes. So then we are going for balance. So again, we have achieved a non-zero bit string state, which is get 1 1, as I mentioned you before. So that is expected because now the oracle is balanced. Okay, for input 0 0. Let us check the other inputs also then. Okay, input 0 1. So this time the X gate will be applied, right? It will be wrapped, right? This is the wrapping. Okay, this one and this one, this is wrapping, remember. And then in between you have the control knots are wrapped between the X gate, right? And bit string is 0 1. Okay, so this time X gate will be applied, right? Look, X gate is applied, right? So it makes sense now. Okay, why we were doing that, and you can compare it with, like, what I have drawn here. You can compare it like this. Okay, so again, like, this becomes, yes. Okay, so 0 1, this is 0 1, and 1 0 I gave you as a homework. You should draw it. Okay, anyways, you will see it now, right now here, but definitely try doing it by yourself. Okay, not by looking at it. I mean, before looking at the answer, definitely, I definitely recommend you give it a try by yourself, and then have a look at the answer if you are not able to get it. That will help you, like, bring confidence in solving the circuits. Okay, so very easy. This code is same only. I have already explained this code. We are just composing that balanced oracle in the circuit and just plotting it and taking the measurement. So it's the same thing only. Okay, not much difference. You can see the wrapped X gates here. Look at the arrow. Look at my arrow. Here is the wrap X gate. Okay, for the C naught. Okay, this is the C naught, and this is another X gate. Okay. So yeah, then Hadamard, and then again the same process. Hadamard applied to only the first register, second register, nothing is applied, nothing is measured, nothing is done. And yes, and then we get the result 1 1. I mean, this is expected because now we are dealing with the balanced oracle. So you will get 1 1 for 1 0 also. Okay, for 1 0 it will be like this. Okay, so I'm not going to explain the code because this is the same code. We are just changing the bit string here. Okay, the other things remain the same, nothing is changed. Okay, so once you know the basic code, then it is easy only. Okay, and then again, this is the same circuit, and you run it with Cosm simulator, you get 1 1. Similarly for inputs 1 1, you can do it again. So this time, this is the same circuit which we drew in the morning. Look, this is the same one. Okay, so we have verified, like, we have verified practically that indeed, like, what we are studying can be implemented, and it indeed gives us those results which we have found out by doing theoretical analysis. Okay, so this is the full circuit, and again 1 1. Okay, this is the general function. Just like for constant oracle we get a general function, here also we get a general function where we use the random. Okay, where we generate a random number that tells us like which C naughts will be wrapped in the X gate. Okay, and then you convert that into a bit string, right? We have to convert that bit string and that bit string, then rest of the code is same. Okay, so these two lines are different. We are generating the bit string value based on this random value which we get, which is 1 comma 2 to the n. It will be between 1 comma 2 to the n, and then based on that we apply the same. This is the same code. Okay, again we are creating that gate, okay, that operator. So by creating that also, you can observe one thing. Once you create that two gate, it also looks like the circuit which we have in our theoretical analysis, right? I mean, I draw a box, right? I draw a box, then before that I apply Hadamard, then after that I apply Hadamard and measurements. It looks very similar, right? This is the same code. It looks very same like our uh, theory circuit, right? Looks very same. Okay, this box also we have, right? In our theory circuit we have this box in between, then we have these Hadamards, then we have the Hadamards afterwards, then we apply measurement, right, in theory. So this gives you the feel of your, like, what you have learned in theory. And again, of course, like, you are going to get all the one, like, a non zero bit string state. Okay, and this is the combined function. Okay, this is the combined, like, basically we combined it with if case. So if case is equal to balance, then this is the code for balance. So basically this code is the same, just copy paste it inside the case, that's it, and it will run. You can provide the case here. Look here, I have provided the case and it ran. So I ran it for 10 qubits. Look, this is 10 qubit circuit. Okay, so this is for balance, right? Because I provided the condition as balance. So this is the case. So as soon as I provide balance, it will go inside this function balance, and it will execute all these lines of code, right? So this is how, like, this is how you can get it with the combined function, etc. And this is of course balanced result, all one bit string. And similarly, in this similar way, you can also try to do it for the three qubit case as well, which is all ket 00, then ket 001, then 010, 011, etc. You can do it for the three qubit case as well. Just increase the number. The code is very generalized, so you should be able to do it without any problems. It will go, it will, the n value, if you provide the n value properly, then you should be able to use the n value for all the other cells as well. Okay, so this is the conclusion of Deutsch-Jodza algorithm. And what we saw is that, in summary, we are able to find a constant or a balanced function, which is indeed a very simple problem, but in those days that was a huge deal, because at that time quantum computers didn't existed. Now it exists, but at those times it didn't existed. Just like in today we do not have many advanced computing technology. We do not know what will happen after 30 years. Maybe after 30 years we will have some very different kind of computational technology. So we don't know what will happen after 30 years, right? So similarly, that's why we do a lot of theoretical analysis and see, and maybe after 30 years technology will have a lot more maturity, and at that time maybe we are able to build some much more novel computers, or much more novel objects based on the principles of physics which we cannot imagine right now. Okay, so this is how quantum is. Also 30-40 years ago it didn't existed, but now it exists. Similarly, from now 2022 onwards, 30-40 years afterwards, what exists we do not know. So technology changes fast, right? So let us conclude this lecture here, and I will stop recording and then ask for the doubts. If you have any doubts, please go ahead.